Okay, so this is the last video for AP Calc BC. After this, you know everything. I mean, of course, my videos skipped over a lot of stuff, and also they're pretty simplistic and confusing, but you know what? I tried. And you know what? You did too. This is a hard class, and I'm very proud of each and every one of you for making it this long. We've gone far, kids. But now it's time to, first off, ignore this, because this is going to be for later. I am going to teach you two concepts in this video. This video might be a little long, so I kind of want to do the rest of this in one video. We're talking about arc length of a polar, and then we're going to be talking about area for a polar, which is a little confusing. Actually, not confusing at all, but it's a little more thought-provoked. So first off, I'm going to teach you the arc length one. So let's say we have r equals cosine of 2 theta, something like that. Which, by the way, if you graph it, it would be a rose that would have 4 leaves, and yeah, be a rose that have 4 leaves. So, the equation to find arc length, I could derive this for you, but I'm not going to. Let's just say that this is from theta 0 to pi over 2. That's what you want the arc length of. If you want the arc length of the entire thing, you would do 0 to 2 pi. But just this, you would do angle 1 on the bottom to angle 2, square root of dr d theta squared plus r squared d theta. Now this may look a little, where did this come from? This is super convenient and awesome, but it's actually a simple proof that I could show you if I had time in this video, but I don't, so I'm just going to tell you this is the equation, memorize it, got it, good. So, for this one, it's an integral, and we're going from 0 to pi, pi over 2. First thing you gotta do, the derivative, which is negative 2 sine of 2 theta squared, plus what r is, which is just the original equation, cosine of 2 theta squared d theta. Boom. That's your arc length from 0 to pi over 2. Isn't that awesome? Yeah, that's arc length. So now it's time to get into the nitty-gritty, and that is the area. Now this is actually kind of, I think it's interesting, but it's going to be a little challenging, and you get a little patience. So, first off, I just want to teach you one thing that's kind of cool. The area of a sector, of a circle, is 1/2 r squared theta. It is, trust me. So, to find the integral, no, I shouldn't say that. To find the area underneath the polar graph, you would do from theta 1 to theta 2, 1/2, which you can always pull out if you wanted to, r squared times d theta. You can picture like this. Let's say you have some weird polar that looks like this, I don't know. What you're doing here is, instead of in the old integrals where you were basically finding tons of rectangles and adding them together, in this one you're finding like tons of kind of like angles and adding them together. That's why the d theta. That's why it's d theta, because it depends on the theta. The width of you want the theta to basically be reduced to nothing. Kind of like how when I explained derivatives to you such a long time ago, nostalgia, very first unit, I said you were kind of doing like a limit, and you want the width of the rectangles to eventually be nothing. It's kind of like the same thing here. So that's how you do this. So for example, if we simply had r equals 4 sine theta, which looks like that. To get this area, we would go from 0 to 2 pi, or wherever you want the area to go to. Actually, you probably should just do 0 to pi on this one, because it only takes pi to get around this. So I'll do 0 to pi, 1/2 up on the outside, 4 sine theta squared d theta, boom. That's area underneath or inside the polar curve. Now, why did I say before it's going to be a little confusing? Well, because they're going to ask you some pretty comprehensive questions with this. Here we go. Let's say you have this line right here that I put off the side, 4 sine of 3 theta. If you don't know what it looks like something like this. And you could totally see if my back wasn't here. It looks something like this. Okay, and where this right here is 4, and each of these is kind of like the distance of 4. So, what if we also have r equals 2, which on polars, it's going to look something like that. The first question, what is the area that is inside r equals 4 sine 3 theta, but outside r equals 2? That would be represented by this. First off, all of these petals have the same size. And because they're all being cut off by something that has a radius that's, constantly the same, all 3 of these sections are the same size. So you can find just one of these and be able to multiply it by 3 to get the total area. The first thing you want to do is you want to know what bounds you're going to have to take the integral for. So you're going to have to find the intersection points. To do that, make these two equal each other. So you're going to get 4 sine of 3 theta equals 2. Sine of 3 theta equals 1/2. When does sine equal 1/2? Sine equals 1/2 at 3 theta equals pi over 6, 5 pi over 6. And then if you divide it by 3, you get theta equals pi over 18, 5 pi over 18. That means that this right here is when theta equals pi over 18, and this right here is when theta equals 5 pi over 18. If you think about it, that kind of makes sense, because this right here would be 9 pi over 18, or pi over 2, so that looks about right. To find that integral, now that we know what the angle is, the first thing you're going to want to do is you're going to want to draw in that angle. So for example, let's draw in super not straight lines, look like that. And now that we did that, is the area going to be covered inside, or is the area that you're finding, is it inside those angles completely? You're probably thinking, well, won't it always be? No, that's why you have to check this. The answer is yes for this one. So it's a simple, you're going to go from pi over 18 to 5 pi over 18 of 1/2. And you want to do the outside and then subtract the inside. Kind of like how back when we were doing derivatives, or the area between two lines, we would subtract the top or the bottom one from the top one to get just what this part is. Does that make sense, kind of? So you want to get this entire area and then subtract this area, so you're just left with this. Also note this is a sector of a circle, so you could just do a sector one, or you could just do it this way too, it's fine. So this one is going to be 4 sine of 3 theta squared minus 1/2 2 squared d theta, and that should give you the area, and then you would multiply that by 3 to get for all 3 of them. Okay, so the last thing we want to do is the thing that makes this a little difficult. Let me just kind of make this look like what I did a second ago. What if the question asked, what is the area of the region that is in both of these? So it'd be like this, and this. This is where it gets a little confusing. So we already found the intersection points to be at pi over 18 and 5 pi over 18, at least for this first one. You could find these two. This one would be pi minus both of these, and we could find these two, but we don't have to because we could just multiply it by 3 to get the area for all of them. The difference here is we're going to draw this in, like I did last time. And I hope you can see this on here. Do you see how the complete area is not inside those angles? Because look, I'll shade it in for you so you can see it a little better. There's these little kind of curved segments that aren't inside those. Alright, here's the deal. First off, you want to get this part right here, because you know how to do that already. It would just be from the intersection point, so pi over 18 to 5 pi over 18, 1/2 times, and this one would be the circle, so it'd be 2 squared d theta. Even though there's no thetas in here, it's an easy one. Okay, so that is going to get you this part. What about these shaded parts? Well, these shaded parts are completely symmetrical, so you can just find one of them and multiply by 2. So you're going to say plus 2 times the integral. And now we just want to know what the bounds are. Do you agree that these are included in this outside polar equation? All we need to know is what the bounds are for these tiny sections, multiply it by 2, and that would be enough for you to be able to find what the small sections are. Well, we know that when is x, that it's kind of starting at 0 and stretching out here until it equals 2, which is the radius. So when is 4 sine of 3 theta going to equal 0? You can do work to find this, but shouldn't you guys realize it's going to be when the theta equals 0? You could do work for this. 0 equals 4 sine You don't even know why I'm laughing because you can't see the board. 0 equals that. Sine of 3 theta equals 0. 3 theta equals 0. Theta equals 0. So, oh wow, look at all that work to find that it starts at 0. Because it starts at 0, that means now you can do an integral that goes from 0 to where this intersection is, which is at pi over 18. 1/2, and then this one would be the 4 sine 3 theta squared d theta. And this will get you this area right here. But once again, there's 3 in this entire thing, so you then take and multiply this entire thing by 3. And oh my gosh, you just finished Calc PC! How does it feel?